Hello everybody and welcome to this presentation which is all to do with understanding and using trigonometric identities. Now in year one there are two trigonometric identities that you need to learn and know about. So in this presentation we're going to derive them both and we're going to look at some examples of how they are useful when it comes to solving trigonometric equations. So let's derive the first one. So I have here a right angle triangle that I've labelled the sides A and B are my two shorter sides. I've got an angle theta and my hypotenuse is 1. So there are a few things we can work out from this triangle. The first thing we can work out is the value of sine theta. So sine theta would be opposite, which is this side here, over hypotenuse, which is this side here. So sine theta would be A over 1, which is simply just equal to A. Similarly, we can write down that cosine theta is equal to B, and we can work that out by doing adjacent over hypotenuse. So the adjacent side to theta is B, the hypotenuse is 1, which gives me cosine theta is B over 1, or just simply put B. The third thing that we can work with when we have our right angle triangle is we can work with Pythagoras theorem. So using Pythagoras theorem, a squared plus b squared would equal c squared, or in this case a squared plus b squared would equal 1. And then if I replace my a and b that I have found already from the previous work that I've done, we can see that by replacing a, b and c with the hypotenuse value of 1, we end up with our first trigonometric identity. Sine squared theta plus cos squared theta is equivalent to 1. Now notice how we haven't got an equal sign here. This is not an equation. We're not trying to solve the equation. This is an identity. So for any value of theta, if I replace theta within this identity, it will equal 1. And by all means try that out with some angles of your choice. So that's our first trigonometric identity. It's not something that we should be solving, but we're going to be using it later on to solve some trig equations. Moving on to my second trigonometric identity. There are other things that we can work with in our right angle triangle. So tan theta would be opposite over adjacent, which would be A over B. So the opposite side is A, the adjacent side is B. And if I replace A and B from the work that I did previous, we then get our second first year trig identity. And that is that tan theta is equivalent to sine theta over cos theta. And again, you can replace theta with any angle of your choice and prove that this works. But this is not an equation to solve. This is an identity that we can use to solve some other equations, which we will be doing in just a minute. Okay, so now that we've derived the two identities, it's now time to look at a couple of questions that would use them. So in this particular question, we're given the value of sine theta, where sine theta is equal to 2 over x, and it says use the trig identities to find the exact acute values of cos theta and tan theta. So we'll do these one at a time. And the way that I'm going to find cos theta is I am going to use one of the two identities that I have just derived. And the one that I'm going to use is this one, that sine squared theta plus cos squared theta is equivalent to 1. So I'm going to replace sine theta within the identity, and then I'm going to be able to rearrange it in order to find eventually the value of cos theta. So sine squared theta would equal 2 over x squared. And then I'm going to square that fraction, and by squaring a fraction I square the top and the bottom of the fraction, and then I'm going to subtract it from 1 to find the value of cos squared theta, which is my next line of working. And then rather than square root both sides at this stage to find cos theta, I am going to write that right-hand side as a single fraction rather than the subtraction that you're seeing there. So my common denominator would be x squared, and then that would create this single fraction, which I'm then going to take the square root of in order to find cos theta. And there's one small extra that I can do to tidy that up, in that if I take the square root of a fraction, I simply square root the top and then I square root the bottom. So the square root of x squared minus 4 is left as it is, but the square root of x squared is simply x. So I've now found my value for cos theta. Okay, and now it's time to find tan theta. And in order to do that, I can use both the sine theta and the cos theta that I've just found from the previous question. And the way that I'm going to find tan theta is I'm going to use my second trig identity, which is this one here. Tan theta is equivalent to sine theta divided by cos theta. So I'm going to replace the values that I've already found into my identity. It looks a little bit scruffy, so I'm going to play around with this, and I know that dividing by the fraction at the bottom and the denominator, so dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So if I multiply by x over root x squared minus 4, the x's are going to cancel and it will leave me with 2 over root x squared minus 4. Okay, there is also an alternative to this question that doesn't use identities at all. So I will show you this method as well. But the only reason why I can use this right angle triangle approach is because I was told in the question that the angles are acute. So if my angles were obtuse, then I wouldn't be able to use this method because right angle triangles don't have any obtuse angles within them. So how can I use my right angle triangle to find cosine theta and tan theta? Well, first of all, I can replace my opposite side of my triangle with 2, and I can replace my hypotenuse in my right angle triangle with x, and that's coming straight from the SOHCAHTOA work that you learnt at school. So this side over here is equal to 2, as that's the opposite side to theta, and the hypotenuse is x. And then from that we can use Pythagoras theorem in order to get our third side of our right angle triangle. So I shall do that. And we would get the square root of x squared minus 4. That's just using Pythagoras. And then as soon as I have my third and final side for my right angle triangle, I can then use SOHCAHTOA in order to get the values of cosine theta and also tan theta. So cosine theta would be adjacent over hypotenuse, which is this side. This is the adjacent side. This is the hypotenuse, and therefore cosine theta would end up looking like this, which we already know because we've derived it in the previous example. And tan theta would be opposite over adjacent, so the opposite side is 2. The adjacent side is the square root of x squared minus 4, and again that gives us the same answer as we had using the other method. So just be aware that if your angles are acute, you can use this right angle triangle method rather than using any of the trig identities. It just depends on the question and the information that you're given. Okay, good. It's time to practice those skills then. So on page 70, there is an exercise on the work that we've just been covering. Have a go at those questions. Any problems, speak to your classroom teacher. Make sure that you check your answers regularly from the back of the book. And once you're ready to move on, I will see you on the next slide. Okay, so now that you've practiced that skill, let's move on to look at a couple more equations which would be impossible to solve without the use of an identity. So here's our first one. We are asked to solve sine theta is equal to 3 cos theta, and again we've got that interval in which we have to write down our values for theta. So initial thoughts might be that we can take everything over to the left hand side to make it equal to 0, but even by doing that there aren't any common factors of the terms, and then there would be little more we can do. So what we're going to do is we're going to rearrange this this equation so that we can then use the identity of tan theta being equivalent to sine theta over cos theta. So taking my original equation, the first thing I'm going to do is divide both sides by cos theta, and then that sets this up really nicely because sine theta over cos theta is equivalent to tan theta. So I can simply replace my sine theta over cos theta with tan theta. And now we have an equation that can be solved fairly straightforwardly using the skills from a previous presentation. So as before, I don't need to draw the graph every time I am asked to solve a trig equation, but I'm showing you this for the purposes of illustration. So I am expecting there to be two solutions between 0 and 360, and I'm going to get my first solution by finding the principal value. So inverse tan of 3, make sure you are in degree mode on your calculator, gives us an answer of 71.6. And then, as we learnt in a previous presentation, we find the second solution for the tan curve by simply adding 180 degrees onto my principal value. So my two solutions are 71.6 and 251.6. Good, and here's our final example. We have to solve the equation sine squared theta plus cos theta equals 1, again between 0 and 360. Once again, initial thoughts might be to bring the 1 over to the left hand side, make it all equal to 0, which would seem like a good idea, but then we have an equation that has different trig functions within it, and there are no common factors, and therefore we would be in a position where we couldn't do much more. So instead we're going to use the second of our identities, which is sine squared theta plus cos squared theta is equivalent to 1, and my aim is to replace the sine squared theta in the original equation. So I'm going to first of all rearrange my identity. So this has nothing to do with the original question. This is just rearranging the identity, and rearranging the identity gives me sine squared theta is equivalent to 1 minus cos squared theta. And then what I can do is I can replace that sine squared theta into my original equation. And by doing that, you can now see that my new equation is completely in terms of a single trig function, and therefore that's going to make this a lot easier to solve. So when rearranged, the 1's cancel and I get left with cos squared theta minus cos theta equals 0. I can then factorize the right hand side. I wouldn't at this stage divide through by cos theta, otherwise I'm going to lose out on some valuable solutions. So instead I'm going to factorize the right hand side, which would give me this, and then that sets me up with two separate equations to solve. The first of them is where cos theta is equal to 0, and the second one will be where cos theta is equal to 1. So going back to my first equation, cos theta equals 0, the first value between 0 and 360 is 90 degrees, and you can work that out on your calculator by doing the inverse cosine of 0, and then our second solution using the symmetry of the cosine curve will be at 270. Cosine theta equals 1, we get an initial value of 0 degrees, and then that leads to, again, some other solutions, or one other solution, which will be 360 degrees. So 0 and 90 are my two principal values for cos theta equals 0 and cos theta equals 1. And then I get my third solution by looking at the symmetry of cosine in relation to the 90 degrees. That gives me 270. And then my final answer will be 360, based again on the symmetry of the cosine curve in relation to the 0 that I found for cosine theta equals 1. So 4 solutions altogether. Good. So our final exercise is on page 79, exercise 4.5. Have a go, look at the solutions regularly in the back of the book to make sure that you have got all of the answers that are required. Any problems, speak to your classroom teacher, and I look forward to speaking to you on the next presentation. So thank you and bye-bye for now.